So yeah, now our character functions. These character functions are just not any functions from G to the complex. They have to have a particular structure, that's group homomorphisms from G to the complex unit circle. And like the group structure is just multiplication of complex numbers here. And we are just going to take all these functions, character functions, and set them into a group which we'll call the dual group. And now this dual group G hat is a abelian group. We can also endow it with the compact open topology, and this results in the group being locally compact. And now we have this locally compact and abelian group G hat, which means we can take its Fourier transform. And you can see repeating the same process, we can find the Fourier transform of that and that and that again. And that might be an issue if we are trying to understand the structure of all these things. So Pontryagin duality is actually going to help us a lot here. Basically, we have a very natural map between very natural relation between G and its double dual, which essentially takes X to a sort of evaluation function, which evaluates X at a particular G. Now, what the Pontryagin duality tells us is that this relation, this continuous group homomorphism, is actually much stronger. It is an isomorphism. So our group G and its double dual is essentially the same group, which is really cool. Now I just got a quick sketch for a proof why this is continuous. If this just looks like pretty drawings to you, do not worry about it. The proof really just depends on knowing the topological definition of continuity, knowing how group homomorphisms can help us here, and knowing what the compact open topology is. And I really just want to showcase how the compact open topology helps us work through these dual groups. So it basically allows us to take an open set like this wall here in the double dual of G to a compact set inside the dual of G. So like going one dual down. And because of the fact that this is compact, we can then cover this with open sets and use the compact open topology again to move to compact sets in G this time. And now to just satisfy all the conditions and get a continuity, we take the intersection of them all, and that's essentially the proof of what's happening here. Now, Pontryagin duality also tells us the Fourier inversion formula. And yeah, this equation you might have actually seen in Fourier analysis in the case of real numbers. Okay, now is a Poisson summation. Before we actually get to it, one small point. We are going to deal with quotient groups. So let's just get some information about that. For G being locally compact and abelian, we know that G quotient H is abelian. We can also endow this group with a locally compact topology. And lastly, we have this formula, which is essentially a way to calculate the integral using an iterated integral. Essentially, what it's doing is if we have this group G, we to calculate the integral on it all, we can just instead calculate the integral on H, and then just sum over all those integrals over the different squares that like G quotient H gives us. Now, short exact sequences. This is actually going to be the heart of Poisson summation. So if we have a short exact sequence here, is just a map from H to G, which is injective, and then G to G quotient H, which is surjective in like a slightly special way. It takes everything in H like through the two maps to identity. Now, what we are interested in is looking at the kind of a dual short exact sequence. So just the short exact sequence consisting of all the duals of these sets. Now, we know what the dual of G is. To find the dual of H, it's really simple. Since H is a subgroup of G, we essentially just take all the elements, think of them, think all the elements in H, think of them as elements of G, and then look at the characters or the duals they have. And the only question is, how do you do this for G quotient H? And in that case, what we do is just define the characters only when the character of H is always identity. Since since this equation, if you want it to be a regular character, it will break into psi of x, chi of x into chi of h, and we would need chi of h to just be identity. So what this basically allows us to do is get a short sequence from the character of G quotient H, and it's going to be an injective map since we are selecting only specific, special characters in the dual of G, and then from dual of G to dual of H is a surjective map. Now, what is interesting is when we look at this in the case of the real numbers. We have these two short sequences, and what ends up happening is that R is actually isomorphic to its dual, and is in fact isomorphic to the exact abstraction we had done in the first line. It's also important to note that we can actually find all the characters in the real for the reals using a single character and just changing the input by like some number. And it's not really useful in the real case because we already have an exact formula for how it is in the reals, but this is going to be helpful when we switch to the Adelics. Lastly, we can also get that our quotient Z, the dual of that, is isomorphic to the integers, and similarly the other way around. And that essentially tells us that these two short sequences that we are looking at in the first place are essentially the same, because we have isomorphisms at all places. And that is really where the Pontryagin Poisson summation, clears stuff up in the reals. So like if you look at it in the whole generality, it's this. I want to say it's a bit of a mess because there's just too much notation here, and I'm not going to go through the proof of it. But if you look at it when X is the identity, stuff gets cleared a little bit. And when we go to the real case, let's just see the facts. We have the Poisson summation. We have that R is isomorphic to its dual, and R quotient Z is its dual is isomorphic to Z. So now if we just set G and H accordingly, we do not get the Poisson summation formula. So what went wrong here? It's not that big of an issue. In our case, our Fourier transform is defined on functions, not on the real numbers that we had started with. So what we can do is just redefine the dual of R. Now that we know that they're isomorphic, we can just redefine it so that they're equal, and then we recover the Poisson summation formula for reals. Okay, now I'm going to go on a slight sidestep and talk about the Adelics. I'm going to make a claim that the real numbers are not as special as we think they are. So to understand that, we really need to see how to build the real numbers from the ground up. So we can very naturally build the natural numbers, the integers, and even the rationals. So for instance, the rationals is the smallest infinite set that contains the integers and in which we can add, subtract, multiply, and divide. However, when we go to create the real numbers, what do? We take our distance function, the absolute value function, and find all the limit points using that. the problem that we have here is that we are choosing a particular distance function. It turns out that the absolute value, although a very natural choice for distance, is not the only one that exists. So what can we do? Um, well, we just consider all possible distance functions together. Um, Not the easiest thing, but Ostrovsky's theorem, I'm sorry, I butchered that pronunciation. It tells us that all the distance functions are just the absolute value on the reals and all the absolute values on the p-adic numbers. Now, I would love to talk about p-adics, but that's going to be a separate talk altogether. But to get a sense of what the distance is on like p-adics, in like the phi numbers, for example, phi is very far from 0. And then if you go to 25, it's actually closer, and 125 is even closer. And yeah, you can see how the whole structure is really different. And yeah, so now we want to consider all these distance functions together. So what we can do is just take the Cartesian product of all these different sets, and that's what we are going to call the Adels. Except we're not going to do that, because unfortunately for us, even though all these sets here are locally compact and we can think about Fourier transforms on them all, because we are taking a Cartesian product here, like an infinite Cartesian product, we lose a lot of information. Importantly, the Adels are not locally compact anymore, and we cannot do all of the Fourier analysis that we have been doing. So what's the fix? The fix here is that instead of considering an infinite product, we consider a finite product of the things that we care about, and then consider all possible finite products. And this term on the right-hand side, it is an infinite product, but it's kind of like a degenerate case, which just helps us fill in the information. The reason an infinite product works here is because the ZPs, the p-adic integers, these are compact. However, these are compact, which plays well with the topological definitions. However, QP, the p-adic numbers, is only locally compact, and yeah, that's the issue. Finally, for Adelic Poisson summation, it actually turns out to be very similar to the real numbers. We just replace the reals with Adels, we replace the integers before with the rationals here, and we get the exact same relations as before. Again, here using the character, identifying all characters with a single one, because we don't actually have a very nice equation for an exact equation for it. And yeah, the all of Poisson summation that we had still works here as well. Now, I'd like to note just one thing here. We are showing Q with a discrete sum, and that's really because the rationals are in fact a discrete set in the Adels, and that's why it's just notated discretely. Yeah, that is it. I'd just like to note, no, I've not made any contributions here. This is not research that I've done. It was a reading course I did with Dr. Johnstone, and I'd just like to thank him for helping me learn all this and all his guidance. I'd also like to thank Dr. Peterson for helping me present, and all of you are here to listen to me ramble. Thank you. Any questions? Yeah.
So on the, can you go back one slide?
Okay, yeah, sure.
Can you explain what you meant by it's a discrete sum? So, I mean, I'm fine with, like, I look at it, and to me it looks like a countable sum, right? And it's fine to do sums over countable sets. Is that what you mean by discrete sum? Sum over a countable set?
Yes. It's also to note that, like, in the Adels, at least I'm pretty sure, I'm not very confident in this. The rationals, I do not think they're a dense set in the Adels, whereas in the real numbers they are, and I think that might be it. but please don't quote me on that. I still need to read more into this. Any other questions? Yeah, thank you.
Okay,